The circular mil is a unit of area specifically designed to describe the cross-sectional area of a conductor. The formula for calculating the circular mil area of a conductor is circular mils equals pi multiplied by the diameter squared, all divided by 4, where d represents the diameter of the conductor in inches, and pi is the mathematical constant approximately equal to 3.14. It's essential to grasp that the amperage rating, often referred to as ampacity, of a conductor is fundamentally determined by its resistance. This resistance is intrinsically linked to the conductor's cross-sectional area. The principle at play here is straightforward. The larger the cross-sectional area, the lower the resistance encountered by the electrical current, and consequently the higher the allowable amperage rating. The resistance of a conductor exhibits an inverse relationship with its cross-sectional area. What this means in practical terms is that if you were to double the cross-sectional area of a conductor, you would effectively halve its resistance. This halving of resistance paves the way for a higher amperage rating. However, a crucial point to acknowledge is that the correlation between amperage rating and cross-sectional area isn't a simple, linear one. It's not a case of doubling one leading to a direct doubling of the other. Several factors come into play that influence the amperage rating beyond just the cross-sectional area. These factors introduce complexities to the relationship. One of the most significant of these factors is the operating temperature of the conductor. As a conductor carries current, it generates heat due to the resistance within the material. The amount of heat generated is proportional to the square of the current. If the conductor gets too hot, it can damage the insulation surrounding it, potentially leading to short circuits, fires, and other hazardous situations. Therefore, the maximum allowable temperature of the conductor and its insulation is a critical limiting factor in determining its ampacity. Different insulation materials have different temperature ratings. For example, some common insulation types are rated for 60 degrees Celsius, 75 degrees Celsius, or 90 degrees Celsius. The higher the temperature rating, the more current the conductor can safely carry. The surrounding environment also plays a crucial role. Conductors installed in free air, where heat can easily dissipate, can handle higher amperage compared to conductors installed in conduits or buried underground, where heat dissipation is restricted. The presence of other heat-generating conductors nearby can also raise the ambient temperature, further reducing the ampacity of individual conductors. The National Electrical Code, or NEC, provides detailed tables that specify the allowable ampacities of various conductors based on their size, insulation type, and installation conditions. These tables take into account the factors mentioned above to ensure safe and reliable operation. For instance, NEC Table 310.15 details ampacities of insulated conductors rated up to and including 2000 volts, with different columns for different temperature ratings. Factors like the number of current-carrying conductors in a raceway or cable also influence ampacity and are addressed through adjustment factors in the NEC. The type of conductor material itself also has an impact. Copper and aluminum are the most common conductor materials, with copper generally having a lower resistance than aluminum for a given size. This means copper conductors can typically carry more current than aluminum conductors of the same size. However, aluminum conductors are lighter and less expensive than copper, making them suitable for certain applications where weight or cost is a major concern. The frequency of the alternating current, AC, flowing through the conductor can also affect its ampacity. At higher frequencies, the current tends to flow more on the surface of the conductor, a phenomenon known as the skin effect. This reduces the effective cross-sectional area of the conductor, increasing its resistance and lowering its ampacity. For high-frequency applications, special conductors such as Litz wire, which consists of many individually insulated strands, are used to mitigate the skin effect. Voltage drop is another important consideration when determining the appropriate conductor size. As current flows through a conductor, there is a voltage drop due to the resistance of the conductor. If the voltage drop is too large, it can affect the performance of connected equipment. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To limit voltage drop, larger conductors with lower resistance may be required, even if the ampacity of a smaller conductor would be sufficient. In summary, while doubling the cross-sectional area does reduce resistance and increase ampacity, the actual increase in ampacity is not directly proportional to the increase in area. This is due to the complex interplay of factors such as temperature, environmental conditions, conductor material, frequency, and voltage drop. The NEC provides guidance and tables to ensure conductors are properly sized for their intended application, taking all these factors into account. Understanding these principles is crucial for electrical engineers, electricians, and anyone involved in electrical design and installation. Consider a practical example to illustrate these concepts. Suppose you have a 250 mcm copper conductor with THHN insulation installed in a raceway with 3 other current-carrying conductors. According to NEC Table 310.15, this conductor might have an ampacity of around 255 amps at 75 degrees Celsius. Now, if you double the cross-sectional area to 500 mcm, the ampacity might increase to around 380 amps. Notice that the ampacity doesn't double to 510 amps, but rather increases by a factor of approximately 1.5. This difference is due to the increased heat generation and the limitations imposed by the insulation temperature rating and the proximity of other conductors. Let's delve deeper into the mathematical relationship between circular mills and the diameter of a conductor. Recall that the area of a circle is given by the formula area equals pi multiplied by the radius squared, or area equals pi multiplied by the diameter divided by 2, all squared. The circular mill area is related to the diameter in inches by the formula circular mills equals the diameter in inches squared multiplied by a constant. This constant is chosen such that a conductor with a diameter of 0.1 inches has a circular mill area of 1. This definition simplifies calculations and provides a convenient unit for specifying conductor sizes. The relationship between the diameter in inches and the circular mill area is therefore diameter in inches equals the square root of the circular mills divided by 1000. Using this formula, you can easily convert between circular mills and the diameter of a conductor. For example, a 250 mcm conductor has a circular mill area of 250,000. Taking the square root and dividing by 1000 gives a diameter of approximately 0.5 inches. Similarly, a 500 mcm conductor has a circular mill area of 500,000, which corresponds to a diameter of approximately 0.707 inches. The increase in diameter is not proportional to the increase in circular mill area, further illustrating the nonlinear relationship. Now let's discuss the practical implications of these concepts in the context of electrical installations. When selecting conductors for a particular application, it's essential to consider the load requirements, the ambient temperature, the installation conditions, and the voltage drop. The NEC provides guidelines and tables to assist in this process. First, determine the load current that the conductor will need to carry. This includes the continuous load, which is the load that will be operating for 3 hours or more, and any non-continuous loads. The NEC requires that conductors be sized to carry at least 125% of the continuous load plus 100% of the non-continuous load. This provides a safety margin and ensures that the conductors won't overheat under normal operating conditions. Next, consider the ambient temperature. If the ambient temperature is higher than 30 degrees Celsius, or 86 degrees Fahrenheit, the ampacity of the conductor must be derated according to the correction factors provided in the NEC. This accounts for the reduced heat dissipation at higher temperatures. Also, consider the insulation conditions. If the conductors are installed in a raceway or cable with other current-carrying conductors, the ampacity must be derated according to the adjustment factors in the NEC. The more conductors in a raceway, the more heat will be generated, and the lower the ampacity of each conductor. Finally, check the voltage drop. Calculate the voltage drop for the selected conductor size and ensure that it doesn't exceed the recommended limits. If the voltage drop is too high, increase the conductor size until the voltage drop is within acceptable limits. In addition to these factors, it's also important to consider the type of equipment being connected. Some equipment may have specific requirements for conductor size or insulation type. Always consult the manufacturer's instructions and the NEC to ensure that the installation complies with all applicable codes and standards. Proper conductor sizing is crucial for ensuring the safety and reliability of electrical systems. Undersized conductors can overheat and cause fires, while oversized conductors can be unnecessarily expensive. By understanding the principles of circular mills, ampacity, and voltage drop, and by following the guidelines in the NEC, you can select the appropriate conductors for any application. Furthermore, consider the impact of harmonic currents on conductor sizing. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as computers, variable frequency drives, and LED lighting. These harmonic currents can increase the heating of conductors and transformers, leading to premature failure. The NEC requires that conductors carrying significant harmonic currents be sized accordingly. In some cases, it may be necessary to increase the conductor size by as much as 200% to account for the additional heating caused by harmonic currents. Transformers that supply loads with significant harmonic content must also be derated or replaced with K-rated transformers, which are designed to withstand the effects of harmonic currents. Another important consideration is the use of energy-efficient lighting and equipment. Energy-efficient devices typically draw less current than traditional devices, which can reduce the load on conductors and transformers. However, some energy-efficient devices may also generate harmonic currents, which can offset the benefits of reduced current draw. Therefore, it's important to carefully evaluate the characteristics of energy-efficient devices before installing them. Surge protection is also an important aspect of electrical system design. Surge protective devices, or SPDs, are designed to protect electrical equipment from transient voltage surges caused by lightning strikes, switching operations, and other events. SPD should be installed at the service entrance and at downstream locations to provide comprehensive protection. The NEC provides guidelines for the selection and installation of SPD. Grounding and bonding are essential for ensuring the safety of electrical systems. Grounding provides a low impedance path for fault currents to return to the source, which helps to trip circuit breakers and prevent electrical shock hazards. Bonding connects all metal parts of the electrical system together to equalize their potential and prevent voltage differences that could cause shock hazards. The NEC provides detailed requirements for grounding and bonding. Regular inspection and maintenance of electrical systems are crucial for ensuring their continued safety and reliability. Inspection should be performed by qualified electricians and should include a visual examination of conductors, connections, and equipment. Maintenance should include tightening connections, cleaning equipment, and testing SPD and ground fault circuit interrupters, or GFCIs. In conclusion, the relationship between circular mills and amperage rating is complex and influenced by many factors. Understanding these factors and following the guidelines in the NEC is essential for ensuring the safety and reliability of electrical systems. By considering the load requirements, ambient temperature, installation conditions, voltage drop, harmonic currents, surge protection, grounding, bonding, and regular maintenance, you can design and maintain electrical systems that operate safely and efficiently for many years. Remember to consult with qualified electrical professionals for any electrical work and to always follow all applicable codes and standards. The information provided here is for educational purposes only and should not be considered a substitute for professional advice. Always exercise caution when working with electricity and take all necessary safety precautions. Electrical work can be dangerous, and it's important to be properly trained and equipped before attempting any electrical tasks. By following these guidelines and working safely, you can ensure the safety and reliability of electrical systems for yourself and others. Furthermore, consider the impact of future load growth on conductor sizing. It's often wise to oversize conductors slightly to accommodate future increases in load. This can save money in the long run by avoiding the need to replace undersized conductors later on. When oversizing conductors, it's important to ensure that the circuit breakers and other protective devices are also sized appropriately to protect the conductors from overcurrent. Another important consideration is the coordination of overcurrent protective devices. Circuit breakers and fuses should be selected and coordinated to ensure that the smallest possible area of the electrical system is affected by a fault. This can help to minimize downtime and prevent damage to equipment. The NEC provides guidelines for overcurrent protection and coordination. Arc fault circuit interrupters, or SIs, are designed to protect against arc faults, which are a common cause of electrical fires. SIs detect the unique characteristics of arc faults and trip the circuit breaker to prevent a fire from starting. The NEC requires SIs in many circuits, particularly in residential occupancies. Ground fault equipment protection, or GFEP, is used to protect equipment from ground faults. GFEP detects ground faults and trips the circuit breaker to prevent damage to equipment. GFEP is often required for large electrical equipment, such as transformers and switchgear. The proper selection and application of protective devices, such as circuit breakers, fuses, SIs, and GFEP, are essential for ensuring the safety and reliability of electrical systems. These devices should be selected based on the specific requirements of the application and should be coordinated to provide optimal protection. In addition to the technical aspects of conductor sizing and protection, it's also important to consider the economic aspects. The cost of conductors and protective devices can be a significant factor in the overall cost of an electrical system. Therefore, it's important to carefully evaluate the various options and select the most cost-effective solution that meets all applicable codes and standards. Life cycle cost analysis can be a useful tool for evaluating the long-term costs of different electrical system designs. This analysis takes into account the initial cost, the operating costs, and the maintenance costs of the system over its expected lifespan. By considering the life cycle costs, you can make more informed decisions about electrical system design and select the solutions that provide the best value over the long term. Sustainability is also becoming an increasingly important consideration in electrical system design. Sustainable electrical systems are designed to minimize their environmental impact and conserve resources. This can include using energy-efficient equipment, reducing waste, and using recycled materials. The Leadership in Energy and Environmental Design, or LEED, rating system provides guidelines for designing sustainable buildings, including electrical systems. By incorporating sustainability principles into electrical system design, you can reduce the environmental impact of your projects and contribute to a more sustainable future. In conclusion, the design of electrical systems is a complex and multifaceted process that requires careful consideration of many factors. By understanding the principles of circular mills, ampacity, voltage drop, harmonic currents, surge protection, grounding, bonding, protective devices, economic aspects, and sustainability, you can design and maintain electrical systems that are safe, reliable, efficient, and sustainable. Remember to consult with qualified electrical professionals for any electrical work and to always follow all applicable codes and standards. The information provided here is for educational purposes only and should not be considered a substitute for professional advice. Always exercise caution when working with electricity and take all necessary safety precautions. Electrical work can be dangerous, and it's important to be properly trained and equipped before attempting any electrical tasks. By following these guidelines and working safely, you can ensure the safety and reliability of electrical systems for yourself and others.